it's time to move to the next talk, which will be given by David Marsan, and the title is Long and Short-Term Nucleation of the 2011 Tohoku-Oki Earthquake.
Thank you, Martin. And first of all, I'd like to thank both Barbara and Jan for organizing this workshop and for inviting me. So I'm going to here talk about what happened before the Tohoku earthquake in 2011. And it's more or less a review talk, including some of our contributions. So from this group of people. That's the outline of the talk. So first I'm going to describe long-term changes in sleep deficit rate that were observed with GPS data lasting over years before the main shock, and we're going to complement this with changes in seismicity rate as well to see in more details what happened closer to the trench. Then what is best known is a slow sleep event that occurred about a month to 2 months prior to the main shock, so I'm going to describe that again. Also in terms of seismicity, that culminated in a large foreshock 2 days before the main shock. And what is interesting is that from pressure gauges, we actually get a rather good view of the post-seismic sleep, and it with very clear evidence of migration, fast migration of the slow sleep. But there was no immediate precursor sleep before the main shock, so hours, 2 minutes, and again, according to the close-by pressure gauges. Okay, so what do we know in terms of coupling? That's taken from 2 different studies, and the second graph here. Okay, the second graph here is redrawn from a paper by Kubas et al. And they both agree basically on the main asperity, separated by strongly coupled areas, more in the north and in the south, going to the Sagami Trough. What is less clear is what happens closer to the trench. This study actually used seafloor displacement, so it's possibly better resolved here, and according to the others, they actually don't need, in order to fit the data, to actually have a strong coupling near the trench. Okay, so this coupling has been evolving over years. So if we look at the GPS data from 4 stations on the coast, that's starting from basically the start of the GPS stations deployment in Japan and in the world in 1996 or 1994 it is. Okay. And going up to all the way to the main shock here. And what the authors did was to remove the co-seismic offset of all the intermediate size earthquakes that occurred close to the GPS stations, and then detrend the time series. But for detrending, what they did was to actually take the linear fit from the earlier part, so from the start of the time series to 2002. And then what you can see is that the trend then changed, and with 2 different behaviors, either in the north or in the south. If you look at the 2 stations more to the south, that's an east-west component we're looking at here, and these 2 stations were actually drifting towards the east compared to the longer time scale, again starting in about 2003, 2004. And the slip rate, as you can see, or the displacement rate from the previous rate is increased by about 1 centimeter per year. So this zone here has been decoupling, while in the north it's actually the opposite behavior. So it's been actually slowing down or moving towards the east, and this corresponds to a stronger coupling here. Okay, so actually this recalls what both Anne and Marianne Métrois showed about in Chile with what happened after the Tarapacá earthquake, which seemingly changed displacement rate of surface stations. Here, the point is that there is no clear origin for this change. There was the Tohoku-Oki earthquake in the north, magnitude 8.3, but it's actually quite far from those stations here, so it's unclear what is the cause mechanism for this. If you invert for all the, using all the stations and looking at this anomalous signal after 2003, what you get is again this image that show that there is a decrease in coupling over this zone here, down deep. The main rupture that will occur subsequently in 2011, and then a recoupling here in the north. What we did was to try to complement this with by looking at seismicity data. If this zone is experiencing a decoupling and there is seismicity in this zone, so you would expect the seismicity to actually accelerate over this time scale, while here you would expect exactly the converse, to seismicity to decelerate over time. So that's something we studied. And this is basically the map we get. So it's looking. So it's not exactly the same period of observation. So that's starting earlier in 1990 to 2011, and taking magnitude 3 and above earthquakes from the JMA catalog. So what we did was to actually first to decluster the data, because you have to get rid of the aftershock component. And so some parts here are not well resolved because we use several different declustering methods, and they don't agree, basically due to the fact that there are relatively strong main shocks here, so they don't agree about with the modeling of the aftershock sequence here. So we don't display what happened here because there are doubts. But what you see is mainly a large zone of deceleration here, so going and all the way to the trench. Over 20 years, and it's actually a very strong deceleration. And you get some acceleration actually in down deep, which corresponds more or less to what the GPS sees. If we, for example, look at one specific zone, so it's taken from this part here, so really in the blue area, so that shows this deceleration. So that's here, that's a little bit off the Senriku rupture, and that's the time series of all the earthquakes from 1990 to 2011, magnitude 3 and above. And you actually can see, without doing the declustering, that's the declustered time series, you can actually see that it's decelerating. So if you look at the slope here, on the slope here, and so on, you see that it's actually decelerating over time. So when you decluster, you actually enhance this deceleration. And what is interesting is that it seems to start relatively strongly in about 1998, which, according to Heikki, corresponds to the termination of the post-seismic slip of the Senriku earthquake. So the yellow dots here are the aftershocks of the Senriku earthquakes. It's 10 days of aftershocks, and there was a deeper aftershock here, so extending the aftershock zone towards the coast. But the Senriku earthquake actually really ruptures this part only, but the signal we get is as a wider extent. So it's difficult to really understand what can cause this type of deceleration, but it is observed. Okay, now what is best known really is, because it's been documented in several studies, is a slow sleep event that occurred in January and February 2011, so starting 2 months before the main shock. And if we were 10 years ago, and I would have asked you where you think a slow sleep event would occur in a subduction zone, and my guess 10 years ago again would be that most people would say that slow sleep events are more likely to occur in a transition zone. So when the coupling goes from 1 to 0, so along the coast here of Japan in this zone. And that would be guided by what we know of from past earthquakes. So for example, the 1960 Chile earthquake, or also from the Tonankai 1944 earthquake, for which the co-seismic rupture is located in a shallower part here, but for which we know there was a very significant and strong slow slip down deep, possibly 2 meters in about half a day. And that's taken from a paper by Linde and Sachs, where they used the data we have from this, which correspond basically to a leveling survey. Now we know that that's exactly the same dislocation that Linde and Sachs found. And you can see it's located at a depth where we know that the coupling is low, and when there are clear signs of slow sleep phenomena, including non-volcanic tremor and slow sleep events. Here, the case of the Tokai slow sleep event is a bit special because it's a very long slow sleep event that lasted 4 years. But possibly what happened before the 1944 main shock was a slow sleep event of a very different duration and sleep rate. But with the Tohoku earthquake, we didn't get something like that. What we observed was a slow sleep, but very close to the trench. So really in a shallow part, not at all in a down deep part of the fault. So that's the seismicity for 2 years, 2009, 2010, from magnitude 4 and above. That's the epicenter of the magnitude 9 here. And if we look at this rectangle here, which will host the slow sleep event, there's very little seismicity. And as you can see, there's very, very little seismicity along the trench, which points out to the possibility that it's slowly, weakly coupled. Now, that's the first 2 months of activity in 2011, and you see the seismicity focusing on this zone here, which is about 40 by 40 kilometers wide. And then magnitude 7.3 and its aftershock sequence, and you can see the big magnitude 6 earthquakes here that actually extended the post-seismic phase really close to the epicenter of the magnitude 9. So that's the time series from 2010 to the main shock, and it's actually a time series of detection using template matching with an array-based method, and that's a study by Blandin Gardonio, which has been submitted. And you can see that it's slowly accelerating, and the acceleration gets very, very strong, and that's a magnitude 7.3 here. So it's a very strong signal. If we look again at the seismicity in the 2 months, so before the magnitude 7.3, the big foreshock, so that's again, that's a map view. The activated area here is about 40 by 40 kilometers, as I said, and that's only the magnitude 4 and above, and there were 11 such earthquakes from magnitude 4 to magnitude 5.5 in the space of 2 months. Some of them could be aftershocks, as they are relatively close by, but the zone is actually too wide so you cannot explain the whole the activation of the whole zone by just stress transfer. So you need something else. And so it seems to be a clear case of just looking at the seismicity without any other data of a seismic swarm. And if we look back in time, so that's a yearly activity from 2000, and that's only 2 months of activity before the main shock and before the foreshock, the magnitude 7 foreshock in 2011. That's again the same zone here. The trench is somewhere here, going this way. And you see that this place was actually activated in the past, in 2008, in 2005, and 2003, for example. So we can ask whether what we see here is really some anomalous feature or not. And this is something that we tested, statistically speaking. And in order to do this, what you need to do again is to decluster the data, because you want again to get rid of the aftershocks. So that's what we did. That's a raw seismicity, again with peaks in 2005 and 2008 and 2002 or 3. And if you look at the declustered time series, it's much flatter, but you still get a sense of the acceleration at the very end, so corresponding to the slow slip in 2011. And it's best seen if you actually compute the rate instead of just looking at the cumulative time series. So that's the same data, but shown as a rate, 1 per day. And you need a smoothing in order to show this. So it's been smoothed at 50 days here and about half a year. So 50 days, more or less the duration of the slow slip. And you see the signal is actually strong, while in 2005 and 2008, there's no signal. So you actually, the activity that we observe in this zone before is clearly not due to background seismicity, an increase of background seismicity, so it can be explained by stress transfer and aftershock sequences. Okay, so now the magnitude 7.3 occurs, and with a bunch of aftershocks, so that's including some relatively strong aftershocks up to magnitude 6.8. That's in time, 2 days and a half of activity, leading to the magnitude 9, and that's in latitude. And if you look at a map view, that's the first day after the big foreshock, and then that's the second day. You clearly see a migration. Well, you could think that's a co-seismic, or that's a co-seismic rupture area here, and the post-seismic would extend the zone more towards the south and to up deep. So it's a very clear sign of migration. And actually, if you look at other instances of magnitude 7.3 earthquakes in this zone, you can actually look at 2 other cases that occurred after the magnitude 9. So they don't have the same mechanism, but that's exactly the same area as the one before the main shock. So again, that's here in blue, that's half a day of activity. So again, we see the main patch of activity, early aftershocks, and then the aftershocks extending over 2 days, really outwards. And if you look at these other earthquakes, exactly the same magnitude, although they don't have the same mechanism, you see that there is basically no observable migration. So it's really a remarkable feature to see this spreading of the activity over time in such a short time scale. And this agrees well with what has been observed from pressure gauges, so measuring changes in seafloor elevation. And from those gauges that I don't show here, I think that correspond to those squares here. So that's taken from a paper by Ota et al. So there were all these gauges close to the very on the spot, really. And if you use this signal, you can invert for the co-seismic slip and for the post-seismic slip. So the post-seismic really going towards the south and up deep again, really like what we see with the seismicity. Okay, so this is a clear and remarkable feature from the aftershock sequence, and you really have to look at the migration. That's a remarkable feature for this sequence. If you look at just the time series of the aftershock, there's nothing special about it, and so that's something we did with Bogdan Enescu a few years ago. And in order to look at the time series, you have to actually do better than just looking at the JMA catalog, because it's only complete at magnitude 4.2 for this short period of time. And what we did was to use broadband stations, so the closest broadband stations here, and just looking at the envelope, so the mean envelope after smoothing. And what you get here is just a snapshot, 2 hours of activity. And that has been calibrated in terms of the JMA magnitude equivalent. So we're looking here at, that's a 6.8 aftershock here that I showed you earlier on, and that's a previous 6 point something aftershock. And so in blue, you have the envelope that shows you all the various events, and you can detect new events. And what is more interesting even is that you can actually account for the fact that for example, in the coda of the magnitude 6.8, you're not going to observe any of the small shocks because they're totally hidden. So what you do is that you can actually use the envelope in order to correct for the fact that you won't detect anything, and you do this using the Gutenberg-Richter law. So you extrapolate the Gutenberg-Richter law in order to account for undetected seismicity. And this is something we did, and to make it short, so it's a purely temporal model, not accounting for space, because we didn't relocate the newly detected events. But what you see is that you can actually model the whole time series with an ITAS model, so aftershocks triggering over aftershocks, without needing any changes in background seismicity. So the temporal evolution is really one of a normal aftershock sequence. It's only the migration that is really remarkable. Okay, and again, the migration was observed for the aftershock sequence that's taken from the well-known paper by Caddo et al. So that's the aftershock sequence of the magnitude 7.3, and you see clearly the migration, and it does indeed correspond as well to the migration that was observed on the seismicity data during the slow sleep event. Okay, so again, there were pressure gauges, and they were used to search for anomalous signals, and that's what Ito et al. Did in their EPSL paper. And they found 2 cases of slow sleep events from the pressure gauges. So if you look at this station here and this station here, and what they did was to, well, first of all, remove all the signals they didn't want to look at, so including tidal effects and so on. And then if you look at the difference between those 2 stations, that's what you get here. That's a time series in days. Well, that's starting in 1st of January 2010, so that's the start of the year 2011 is somewhere here, and what you see is a clear departure of the previous trend in sometime in February 2011. So there is a geodetical deformation observation of what happened during the slow sleep. They actually found another instance of a slow sleep event in the same zone, and that's in 2008. And that's associated with a swarm in activity, according to them, but actually that started after the slow sleep event. If you look at the magnitude here, we are at magnitude 6, and then magnitude 5 here, and that actually corresponds to those guys here in map view. And these are just a normal aftershock sequence. So the magnitude 6 triggering its aftershock. So if you actually decluster, and again, that's the same time series as I showed before. In 2008, after declustering, there's nothing remaining, really, no anomalous signal. So we don't actually think that that corresponds to a seismic swarm as we understand them. So maybe there is a slow sleep event, but not associated with a seismic swarm. Okay, and then again using the same pressure gauges data, you cannot see anything special really immediately before the magnitude 9. So again, that's a magnitude 7.3 here, and that's a model for the post-seismic slip. And given the uncertainty on the data, and the uncertainty is actually quite big, it's about 2 centimeters. So you can see the noise here. You cannot really spot anything, any signal before the magnitude 9. And they concluded that they would have resolved something at seismic magnitude 6 to 6.2. So if something happened, it's smaller than this. Okay, so now if, again, we try to estimate the seismic moment of the slow sleep event that lasted for 1 to 2 months, we have different estimates that actually converge. So again, if you use Ito et al. Estimate, it's magnitude 7.0, but it only lasts about a week, according to them. If we use estimate by Kellogg et al. Using repeating earthquakes and exploiting the Nadeau-Johnson relationship, you end up with magnitude 7.1. If you only actually sum up the magnitude of the seismicity that comes along this slow slip, you have a total seismic moment of 5.7, but then we know that this only accounts for a small part of the deformation. And typically, during seismic swarms, what we observe is that the seismic part of this total seismic moment only accounts for a few percent. So that's a rough estimate that really depends on the slow slip. But if we say that seismicity only accounts for 3% of the total moment, we end up with 6.7 as an estimate. And if we say it only accounts for 1%, we get closer to what other authors did. So it's likely that the seismicity only accounts for about 1% of the total deformation. Now, so really to compare with what could be done, well, it's something very peculiar because that was at the end of World War II, and it was very lucky that there was a leveling survey taking place the day before the main shock before the Tohoku-Oki earthquake. But at the time, people could actually spot a magnitude 7.8 slow sleep event occurring within 1 day, basically under the feet. While nowadays, well, I mean, again, that's, instrumentation has changed quite a lot, but we can spot slow sleep events that have slow moments and that last for a much longer period of time. So you're talking about much lower seismic moment release rate, and again, closer to the trench. And hopefully the SNET data will help resolving these shallow slow sleep events. So I'm going to conclude with a couple of slides. So we can say quite a bit about the kinematics. So identify and characterize slow sleep events, even at in the shallow part of the fault, but we understand very little about the dynamics. And we really don't know what causes this transient slow sleep. Just a few hints. Again, that's magnitude 9, that's magnitude 7.3 for shock epicenters. And if I plot this along with the redrawn map from the seismic coupling of Kubas et al., we see that they seem to occur close to a change, a transition between fully locked and the unlocked part close to the trench. We actually looked at other cases of swarms in the past in the whole area, just based on seismicity, and what we found was 9 cases of significant, 9 cases for which we are fairly sure that there are seismic swarms. So starting in 1999 and up to 2011. So 4 of these swarms actually in the outer rise. And well, I mean, they're very different mechanism, likely. And 5 others, there are 5 cases of swarms in this observation time in this area, and 2 of them actually, the last one corresponds to the one before the 1999, but the first one is actually, it's not clear, but it's located in the same area. So the same area actually has hosted 2 seismic swarms. The last one is for sure related to slow slip, so we can guess that the first one was as well related to slow slip. And there are other cases here, and here, and if I locate them on the coupling map, well, I mean, it's not extremely clear, but we can guess that they correspond to places where the coupling gradient is strong. And again, this that we know very well, and there was very strong, very large co-seismic slip in the zone, and obviously a very large stress drop, and that's taken from a very nice paper by Nakamura et al., published last year in JGR, where we see seismicity before, and in blue you have interplate thrust mechanisms on the slip interface, and that's the aftershock part, and all the blue here in this part revert to green normal earthquakes actually occurring below, underneath the plate, the subducting plate, and the whole zone here was has been shut down in terms of the seismicity, so very strong stress drop. So we know it's a place that can slip a lot, and if we look at friction sliding friction experiment made in the lab, using a sample that was drilled close to the trench, so taken from the fault core, and Ikari et al. Did velocity change experiments, and if you look at the response of the sample when you decrease the velocity, so it's actually in the long term is strengthened, so it's actually a velocity weakening property. But what is interesting is that if you zoom in, well, you don't really see it, but immediately after the change in velocity, you get stick slip, so velocity weakening behavior. But then also, if you wait for a longer time, you will see spontaneous slow slip events, micro slow slip events developing with 2 instances here in this time series. So the same sample can undergo velocity weakening and slow slip events. So and it's there is a slip dependency on the frictional property here. So to conclude, we've seen that slow slip can occur at shallow depth, and Jean-Mathieu Noquet also showed other examples in Ecuador earlier on this morning. They can trigger swarms, even though some could possibly have occurred with a triggering swarm, and that's 2008 slow slip taken from Ito. No swarm during the slow slip event. They can repeat over many years, so in the same zone as 2011 slow slip, there was possibly one in 1991. And they occur near large coupling gradients, and they can trigger very large earthquakes. But and then there could be an indicator that the zone is actually a low friction zone that can slip a lot during the co-seismic rupture. Okay, thank you for your attention.